This is lesson 4, applications of vector addition, and we're going to be looking at force, velocity, and tension applications of vector addition. So this is from the grade 12 Calculus and Vectors course, and it's from Unit 4, Geometric Vectors. So make sure you've gone to the link in the description, you've got a blank copy of the lesson ready, and you can fill it out as we follow along. So let's get started. Part 1, resultant forces. So I would take a minute, pause the video, and read this section here. But what this section is talking about, it's specifically talking about what a resultant force is and how we can calculate them. So remember, a resultant is the sum of two vectors, two or more vectors, right? So if I have, let's say, a force vector here and a force vector here, placed tip to tail, the resultant of those two forces is this vector here, the vector that goes from the tail of the first force to the tip of the second force. And we would call that the resultant force. So, we've got force 1, force 2, and the resultant of those two forces would be this here. And often in the questions in this section of the course are going to give you information about forces or velocities or tension vectors, and we're going to need to compose them so that they are placed tip to tail and calculate the resultant vector, both its magnitude and direction. So let's get going with some of these types of questions. I'm going to take you through a few examples. Example 1. A sailboat's destination is 8 kilometers east and 6 kilometers north. Find the magnitude and direction and bearing notation of the resultant. So a sailboat's destination. So it's going 8 kilometers east, so magnitude 8 kilometers, direction east, so I can draw a vector that is going east, and it has a magnitude of 8 kilometers, so I'll label its magnitude 8 kilometers. And the destination is also 6 kilometers north, so I can draw a vector that is magnitude 6 kilometers going north. And when I draw this vector, I'm going to draw it so that it's tip to tail with this vector so that I can easily find the resultant. So this drawing isn't necessarily to scale, but as long as I have the correct labels on here, I should actually be able to calculate the resultant. Remember, a resultant vector is the sum of these two vectors. And when adding vectors, they have to be placed like they are right here, tip to tail. So now the resultant goes from the tail of the first vector to the tip of the second vector. So let's see what that resultant looks like. So this is the resultant vector. Now what I need to do is find out its magnitude and direction. So figuring out its magnitude is fairly straightforward. This is a right angle triangle. Since these directions were east and north, I know it forms a 90-degree angle. I can just use Pythagorean theorem to find the magnitude of the resultant. And remember, we use absolute value symbols to indicate we are looking at the magnitude of vector r, the resultant vector. So the magnitude of this side, what's its relationship to these sides? Well, remember Pythagorean theorem, the sum of the squares of the legs equals the square of the hypotenuse. So the magnitude of vector r squared equals 8 squared plus 6 squared. And then if I evaluate this, 64 plus 36 is 100. Square root that, I get the magnitude of r is 10 kilometers. So I now know the magnitude of this. But I also want to describe its direction. So in describing direction, there's different ways of doing it. Quadrant bearing, true bearing, angle from a horizontal. What I'm going to do for this one, I'll do true bearing. So to describe a true bearing, that means from a north line, what is the angle clockwise to the vector? So let me just draw in a north line so we can see what we're working with here. So here's a north line. And what I want to do is describe the angle, this angle here, clockwise from the north line, and that's its true bearing. So there's a few ways we could calculate this. I think the easiest way to notice that this line and this line are parallel to each other. So we could use a parallel line theorem. I know that this angle and this angle are equivalent to each other. They're alternate angles. They follow that z pattern. So I can calculate this angle using trigonometry, and I know it's equivalent to that angle. So I will use, since I want this angle, and I know all three sides of the triangle, but it originally gave me these two, so I'll use these two sides. From this angle, this is the opposite side, this is the adjacent side. The trig ratio that has opposite and adjacent is tan. So I know tan of the angle equals opposite 8 over adjacent 6. And I can calculate the angle that has that ratio by using the inverse tan ratio. So inverse tan of 8 over 6 will give me the angle. And I'll get an approximate angle. So let's And we'll calculate the angle in degrees. We'll work in degrees for this section of the course. So on my calculator, I'll do inverse tan of 8 over 6, making sure I'm in degree mode. And I got about 53.1 degrees. So we can summarize our answer now. So we can describe the direction and magnitude of this resultant vector. So our final answer would say the resultant is 10 kilometers, that's its magnitude, at a true bearing, right, we have to describe its direction as well, of 53.1 degrees. Right, as a true bearing, you always have to give your angle with 3 digits. So we have to put a 0 in for our hundreds column. So here's our final answer. Example 1 is done. Let's move on to example 2. Part 2, velocity. So the next example we're going to do is about velocities of airplanes. And we're going to need to understand a few specific words that have to do with velocities of airplanes, specifically air velocity, wind velocity, and ground velocity. Before I talk to you about that, feel free to pause the video and read this section here, which just reminds you that when we're talking about resultant velocities, we're talking about the sum of multiple velocities. Just like with resultant forces, we were talking about the sum of multiple forces. So let's look at this diagram I have drawn here. So when we're talking about the velocity of an airplane, usually we're talking about the air velocity of the airplane. That's its velocity relative to the air that it's flying in. And that's what this section explains to you here. Now, someone from the ground wouldn't be observing a plane's air velocity. They'd be observing what we would call ground velocity. So if you're on the ground observing a plane flying, the velocity you are observing is the velocity that is the sum of the plane's air velocity, the velocity relative to the air it's flying in, plus the velocity of that air. The velocity, we call that the velocity of the wind. So this formula down here, the ground velocity of an airplane being equal to the sum of the air velocity of the airplane plus the wind velocity, is the formula we need to understand. Right? The velocity we would observe of the plane from the ground is equal to the sum of its air velocity plus the wind velocity. So understanding this formula is going to be foundational to us doing the next example. So let's give the next example a try. Example 2. A plane travels north 40 degrees east at an airspeed of 1,000 kilometers an hour. So in the air that the plane is flying in, it's going at 1,000 kilometers an hour in this direction, north 40 degrees east. Measurements on the ground indicate that the plane is traveling north 45 degrees east. Okay, well, it's going in a different direction, so the wind must be affecting it. And it has a different speed, right? Its magnitude is also different. Its magnitude is increased. So the wind must be changing its direction and increasing its velocity. So what velocity of the wind does that? So in order to calculate this, we should start by drawing a diagram. So it gives us the directions in quadrant notation. So we should draw a Cartesian grid to help us visualize this problem. And I'll just make a big diagram to kind of exaggerate this for us. So here's my Cartesian grid, and up top I have north, east, south, west. I know that the airspeed of the plane is 1,000 kilometers an hour, that's its magnitude, at this direction, north 40 degrees east. So let me draw a vector that meets that criteria. And I'll place its tail at the origin, right? The position of the vector itself doesn't matter. So it's probably easiest if I draw it with its tail at the origin. That makes it easiest to draw the direction. So let me do that. So this is my airspeed vector, so I'll label this the airspeed vector. Now the ground speed, what someone is observing from the ground, is different. So let me draw that one, right? The direction is now north 45 degrees east. So instead of the airspeed vector, which was 40 degrees towards east from north, I now need to draw a vector that's 45 degrees towards east from north. And it needs to be slightly longer. So let me go ahead and draw that. So it's 5 degrees more towards east, and it's slightly longer. I'm going to exaggerate this just so we can have room to write in our diagram. But this angle in here is only 5 degrees. The angle in here is only 5 degrees. I've exaggerated it so I had room to write. This is our ground velocity, so I'll label this vector v with a subscript ground. And the question is asking us, it's saying, what would be the velocity of the wind? And remember, velocity is a vector. It has a magnitude, a speed, and a direction. So I need the speed and the direction of the wind vector. And remember this formula over here. The ground velocity is the sum of the air velocity and the wind velocity. So I know that this, the blue vector, is the resultant, the sum of air velocity plus wind velocity. So I need to draw a wind velocity vector tip to tail with the air velocity vector, where the ground velocity vector is the resultant. So let me draw in the wind velocity vector. I'll label this vector W for wind. And notice how I have my diagram set up. I have the air velocity plus the wind velocity is equal to the ground velocity, right? The wind is pushing that airplane 5 degrees more towards east, and it's also making its magnitude slightly bigger. I can label the magnitudes of these vectors too. That might help with our diagram. Okay, so I want to figure out, let's start with the magnitude of the wind velocity. So if I want the magnitude of this, well, this is not a right triangle, or not, at least not that I know of. So I can't use SOHCAHTOA. So I'm going to need to either use cosine law or sine law, depending on what information is given. So notice I'm given two sides and a contained angle. That's the criteria for cosine law. Cosine law would allow me to calculate the side opposite from the contained angle. So let me write out how I would calculate this using cosine law. So based on cosine law, I know the magnitude of vector W squared would equal 1,000 squared plus 1,050 squared minus 2 times the product of those two sides, 1,000, 1,050, times cosine of the contained angle, so times cosine of 5 degrees. And now I just have to evaluate this, square root it, and then I have an approximate value for the length of that side, so the magnitude of the wind velocity. So let me evaluate this on my calculator and get an approximate value for the wind velocity. So in my calculation, I got the magnitude of the wind velocity to be about 102.4 kilometers an hour. So that's the magnitude of that vector, but when describing a velocity, you also need its direction. So I need to figure out what direction is this vector going in. So when describing a direction, we can either describe it in true bearing notation or quadrant bearing notation. For this one, I think I'm going to describe it in quadrant bearing notation. So to do that, often for these types of questions, it's beneficial to draw in some imaginary vertical or horizontal lines, because the angles that are given to us, those angles actually are in relation to north or south or east or so on. So they're in relation to vertical and horizontal lines. So we know what angle vectors make with vertical and horizontal lines. So let me show you what I mean. Let me draw an imaginary vertical line here. So with this imaginary vertical line, I know that based on parallel line theorems, right, based on the z pattern, let me just use a highlighter here to show you, based on the z pattern, since this vertical line and this vertical line are parallel, I know that alternate angles within there are equal to each other. So that would tell me that, and let me change back to my pen here, that would tell me that this angle and this angle are equal. So I could label this angle in here 40 degrees. That's a good starting point for describing the direction of this vector. But like I said, when I describe the direction of this vector, I'm going to describe it in quadrant notation. So this vector is going south and then a certain number of degrees towards east. I need to figure out what is the degree measure in here. And I'll call this alpha. I want to figure out that degree measure. Notice if I had this entire angle, I could just do that angle minus 40 and that would give me alpha. And then I could say south, alpha, east. And that would give me the direction of that vector. So let me calculate this whole angle. Let me call this whole angle, I'll call that whole angle angle theta. And since I know all three sides of a triangle, I could use cosine law to calculate an angle. If possible, we want to avoid using sine law to calculate an angle. Because remember, when you calculate an angle with sine, with sine law, you have to consider the ambiguous case of sine. So unless you want to have to consider that, it's best to just use cosine law, where it'll give you the only option for the angle. So let me use cosine law to calculate angle theta. So cosine of theta equals, well, how cosine law works is you do the side opposite from the angle you want, so 1,050 squared, minus the squares of the other two sides. So minus 1,000 squared minus 102.4 squared. And you divide that by -2 times those second two sides, times 1,000 times 102.4. And now this is the cosine ratio. If we want the angle, we do inverse cosine of that ratio. So let me calculate that. So I calculated the angle to be about 116.7 degrees. So theta equals 116.7 degrees. So that's this entire angle theta, that blue one there. But when describing the direction, I only want alpha. So when I calculate alpha, in the diagram you can see that alpha was equal to theta minus 40. So I have to do 116.7 minus 40. So 116.7 minus 40 is 76.7 degrees. So now I can describe the velocity of the wind. The velocity of the wind is 102.4 kilometers an hour at a quadrant bearing of south 76.7 degrees east. So that's example 2 done. We found the magnitude and direction of the wind. Part 3, equilibrant vector. So this is an important concept that we're going to need to understand to do examples 3, 4, and 5. So let's read this together. An equilibrant vector is one that balances another vector or a combination of vectors. It is equal in magnitude but in opposite direction to the resultant vector. So for example, let's look at this diagram down here. I've got these two forces being added together, and here's the resultant of those two forces. So this right here, that's the resultant. Now when we talk about an equilibrant vector, it's equal in magnitude to a resultant vector, but in the exact opposite direction. So that's why it balances a system. And when I say balances a system, it keeps it in a state of equilibrium, meaning it keeps things stationary, right? Because if we add a resultant and an equilibrant vector, well, the sum of two opposite vectors is the zero vector. So the equilibrant of this is just another way of stating the same thing. The equilibrant of a number of forces is a single force that opposes the resultant of the forces acting on an object. When the equilibrant is applied to the object, this force maintains the object in a state of equilibrium, so it keeps it stationary. Example 3. A clown with a mass of 80 kilograms is shot out of a cannon with a horizontal force of 2,000 newtons. So let me just draw that vector for you. Okay, so shot horizontally out of a cannon. Now, that clown, he's not going to keep going completely horizontal forever, right? The force of gravity is trying to pull that clown down. But with what magnitude is the force of gravity trying to pull the clown down? So I should remind you, if we want to calculate a vertical force, right, the force due to gravity on an object, we have to do 9.8, the gravity constant, times the mass of the clown. So just as a reminder for you, the force due to gravity is equal to the mass times the gravity constant. So the force due to gravity, the vertical force in this example, would equal the mass of the clown in kilograms, 80, times the gravity constant, right? The acceleration due to gravity is constant. It's 9.8 meters per second squared. So multiply this by 9.8. And 80 times 9.8 is 784 newtons. So now I know the vertical force acting upon this clown. So I know the force due to gravity. So I can draw that vector. I can draw the vertical force acting on this clown. And since I'm going to want the resultant force, I see that down here, I'm going to place these vectors tip to tail so that I can easily find the sum of the two of them. So let me do that. Okay, so I have my horizontal force and my vertical force. Part A says find the magnitude and direction of the resultant force of the clown. So resultant force, right, is the sum of two forces. That's why I placed these two tip to tail so that I could find the sum of these two forces. So the resultant force would go from the tail of the first vector to the tip of the second vector. So let me draw that. So I want the magnitude and direction of this force. So let's start by labeling this. I'll label this a resultant force. So I'll label this vector r. Let's start by finding its magnitude. Now notice since there's a horizontal and a vertical force, I know those make an angle of 90 degrees with each other, so I could use Pythagorean theorem to solve for the magnitude of this side. So the magnitude of vector r, right, the absolute value symbols mean magnitude. Magnitude of vector r squared equals the sum of the squares of the shorter two sides. So 2,000 squared plus 784 squared. And then I can calculate this sum and then square root it to get an approximate value for the magnitude of vector r. So let me calculate that. So I get about 2,148.2. 2,148.2 newtons. So that's the resultant force. Now I need to figure out the direction that goes along with that magnitude. So if I want the direction of this vector, like I said, there's a few different ways we could calculate this. If I want to describe this as a quadrant bearing, what I could do is I could draw an imaginary vertical line here. Right here would be south, and I could then calculate, well, this resultant force is going south, but a certain number of degrees towards east. And this angle here, if you remember your parallel line theorems, would be equal to this angle right here. So let's calculate theta. So if I calculate theta, I could use sine, cos, or tan since I now know all three sides of the triangle, but I'll use these two sides since that's what the question originally gave me. So from this angle, 2,000 is opposite, 784 is adjacent, so I can use tan. Tan involves opposite and adjacent. So tan of the angle would equal the opposite side, 2,000, over the adjacent side, 784. And then I can calculate that angle by doing inverse tan of that ratio. So I get about 68.6 degrees. So the magnitude and direction of the resultant force, I could say the resultant is 2,148.2 newtons at a quadrant bearing of south 68.6 degrees east. So there's my final answer for part A. Part B says find the magnitude and direction of the equilibrant force on the clown. So remember, the equilibrant force would have the exact same magnitude. It's going to have the exact same magnitude, so I've already got the magnitude of the resultant force, but it's going to be in the exact opposite direction. So let me just shrink this diagram a bit so I have room to draw the equilibrant vector. Okay, so in this diagram, I'm now going to draw the equilibrant vector. So the equilibrant vector is going to have the exact same magnitude of my resultant vector. So let me just go ahead. I'm going to just copy and paste my resultant vector so that I get the exact same magnitude. But I know the equilibrant vector has to be going in the exact opposite direction as that. So I need to reverse its direction. So I'm just going to change the side that the arrow is on. And now here is my equilibrant vector. And let me change its color so we can distinguish it from the resultant vector. Let's make this one a bright green one. So that's my equilibrant vector. Let me just make this even just a tiny bit smaller so that it all fits in the same section here. So I've got my equilibrant vector drawn now. Notice that it's the exact same magnitude of the resultant vector, but it's in the opposite direction. So I'll call this vector E for equilibrant vector. I need to describe its direction. So when I describe its direction, well, remember opposite angles are equal. So this angle here and this angle here are equal to each other because they're opposite from each other. So when I describe the direction of the equilibrant vector, I could say north, theta towards west. So north, 68.6 degrees west. And the magnitude is the exact same magnitude of the resultant vector. So the equilibrant vector is the same magnitude, so I think it was 2148.2, 2148.2 newtons, in the opposite direction of the resultant vector. So at a quadrant bearing of north 68.6 degrees west, right? It's the opposite direction. The resultant vector was south 68.6 east. This is going the opposite direction. It's going north 68.6 degrees west. So that summarizes the equilibrant vector. So in this system of vectors, if I could somehow apply that equilibrant vector to this clown that got shot out of a cannon, it would be stationary, suspended still in air. Example 4. A mass of 20 kilograms is suspended from a ceiling by 2 lengths of rope that make angles of 60 degrees and 45 degrees with the ceiling. Determine the tension in each of the ropes. So for any of these types of questions, like this is a classic tension question, we want to start by drawing a diagram. I'll call it a position diagram that shows what's happening based on how it's described in the question. But then what I'm going to do is I'm going to translate those vectors so that they're positioned in an orientation that allows me to calculate the tension in the ropes. So that means a vector diagram. So I'll keep the magnitude and directions of the vectors the same from the position diagram, but I'll reposition them so that I can actually do the calculations in my vector diagram. So let me start by doing the position diagram, just by drawing my ceiling, drawing the mass of 20 kilograms suspended by the ropes. Let me just draw a rough diagram here for you so I can better explain what's happening in this question. Now that I have this drawn, right, here's my ceiling, here's the mass, here's the 2 ropes. I know that one of the ropes makes an angle of 45 degrees with the ceiling. So 45 degrees with the ceiling. This is clearly the smaller angle in my diagram, so I'll label this one as 45. This is the bigger angle, I'll label this as 60. And I know that this mass is suspended in air, but there is gravity trying to pull this down. With what force is gravity trying to pull it down? What's the force due to gravity acting on any object? Well, the force due to gravity is always equal to mass in kilograms times the gravity constant. So for this question, its mass is 20 kilograms. Multiply that by the gravity constant 9.8, and we get the force due to gravity acting on this object is 196 newtons. So I can draw that vector acting on this mass. So here's the force due to gravity vector. It's pulling it down with a force of 196 newtons. But since this mass isn't moving, I know there is tension in these ropes, right? These ropes are pulling back. So the tension vectors are going to be going in the opposite direction. They're going to be pulling back. So let me draw the tension vectors in these ropes that is keeping this mass stationary. So there's a tension in this rope, and there's also a tension in this rope, right? The ropes are pulling back against the force due to gravity to try and keep this suspended in air. And I'll label these tensions as, I'll call them tension 1 and tension 2. And just a hint for you, the shorter rope, so the one that makes a bigger angle with the ceiling is the shorter rope, is always going to have a higher magnitude of tension. So this tension vector is going to be bigger than this tension vector in terms of its magnitude. So I've called them tension vector 1 and tension vector 2. It doesn't matter which one you call which. But since I know that this mass is suspended in air and it's not moving, it's just stationary there, I know this system of vectors, these tension vectors, and this force of gravity vector must be in a state of equilibrium. What does that mean? It must mean they add up to the 0 vector, which means this one and this one, these tension vectors, must add up to the exact opposite of this vector here, the force due to gravity. Right? In order for this mass to not be falling, these tensions have to be counteracting this force due to gravity exactly. So this one and this one must add up to the exact opposite of that. So when I draw my vector diagram, that's what I want to show. I want to show that this vector and this vector add up to the opposite of that vector, meaning same magnitude, still 196 newtons, but going up. That's what's going to keep this mass from moving. So let me draw that vector diagram. Let me draw tension 1 plus tension 2. Now, I just estimated their lengths over here. I don't know if those are right, so I could change that over my vector diagram. But one thing I do know for sure is their direction. So make sure you keep their directions exactly equal. So I've got tension vector 1. I'm going to keep its direction exactly equal. And I'm going to exaggerate their lengths here, just so we have a little bit of an easier time visualizing the problem. And I've got tension vector 2. And I know those add up to the exact opposite of the force due to gravity. That's what'll keep that mass stationary. So the exact opposite of this one. So same magnitude, but opposite direction. But remember, I'm exaggerating their magnitudes for this. So opposite direction, same magnitude. So I just have to make sure I label this magnitude still 196 newtons to show that its magnitude is the same. 196 newtons. So the vector going in this direction was tension vector 2. And the vector going in this direction was tension vector 1. And I'm interested in figuring out the magnitudes of these two tensions. So if I want the magnitude of this side, well, I'm going to need to know some of the angles in this triangle. And we actually know all of them. I mean, I don't have any of them labeled yet. But if we look over at this diagram, the ceiling is completely horizontal. So I know the angle tension vector 1 and tension vector 2 make with a horizontal line. So over here, I'm going to draw in some imaginary horizontal lines, which is going to actually help us label some angles in the triangle. So now that I have those lines drawn in, let's look at what we know. Well, this vector here, tension 1 vector, with a horizontal line makes an angle of 60 degrees. So I could label this right here, 60 degrees. And this vector here, tension 2, here's tension 2 vector, the direction, with the horizontal line, it makes an angle of 45 degrees. So I can label that 45. And then based on parallel line theorems and some properties of triangles, we should be able to label the rest. Right, here's a Z pattern. So I know the alternate angles inside of that Z pattern are equal to each other. So if this is 45, this is 45. And then let me move this over a little bit so you can visualize the right triangle I have. Right, if you look here, I've got this right triangle. Inside that right triangle, here's the 90-degree angle. If this is 45, then I know this has to be 45 because the angles have to add to 180. And now if we look back at this overall big triangle we have, the entire system of forces that we have, I know that the three angles, this angle, and this angle have to add to 180. So 45 plus 105 is 150, which means that this angle down here has to be 30. So I now know all of the angles inside that big triangle. And I know one side on that triangle. So we could find either of the other two sides using sine law. And using sine law to find side lengths is perfectly fine, right? There's no ambiguous case of sine when we're finding side lengths. It's only when we use sine law to find angles. So go ahead and use sine law to find the magnitudes of tension 1 and tension 2. So sine law tells us that the ratio of the magnitude of a side to the sine of its opposite angle is equal for each pair of sides and angles. So the magnitude of this side divided by sine 30 is equal to the magnitude of this side divided by sine 45, which is equal to the magnitude of this side divided by sine 105. So let me just set up those equivalent ratios for you. So now that I have the three equivalent ratios, I can use this pair to solve for the magnitude of tension 2, and I could use this pair to solve for the magnitude of tension 1. So let me do tension 1 first. So I would multiply this sine 45 over to the 196 over sine 105. So I would get tension 1 equals, or the magnitude of tension 1 equals 196 times sine 45, and we're in degrees, divided by sine 105. And if I calculate this, that will give me the magnitude of tension 1. And let me also set up my magnitude of tension 2 formula as well. So to calculate this magnitude, I would multiply the sine 30 over to that fraction. So I would get 196 times sine 30 divided by sine 105. So I can do these two calculations and get the magnitudes of both of the tensions. And like I said, the magnitude of the tension in the shorter rope should be bigger than the magnitude of the tension in the longer rope. So let's see if we did this properly. So there are my two tensions, 143.5 and 101.5. 143.5, and these are approximate, and 101.5. So the tensions in those ropes are keeping the system in a state of equilibrium, meaning that this mass is not falling at all. It's completely stationary. That vector plus that vector add up to the exact opposite of the force due to gravity, right? It adds up to the exact opposite of it. So let's try one more tension question to make sure you have this, this whole concept down pat. So let's try example 5. Example 5, a video projector of a mass of 2 kilograms is hung by a 5-meter rope from the ceiling. The projector is pulled back 2 meters, measured horizontally, by a horizontal force. So we have some horizontal force pulling back on the projector, so it's moved 2 meters horizontally. Find the magnitude of the horizontal force and the tension in the rope. So let me start by drawing a position diagram, and that's a diagram based on how the question describes our problem. And then I'll figure out what do I need to calculate and how can I reposition those vectors in a vector diagram so that I can do the calculations. So let me start with the position diagram, and then I'll explain further what we're looking for and what the question has given us. So here's my diagram. In my diagram, I have, here's my ceiling. I've got the projector, which, if you can visualize it, instead of being straight down, it's been pulled back horizontally 2 meters from that like imaginary vertical line there. So labeled this side length 2 meters, and the rope that it's attached to is 5 meters long. Now, how is it pulled back? Well, it tells us there's some horizontal force. So let me draw a vector that's completely horizontal that is pulling that projector back 2 meters. So here's my vector that would do that. And I'm not worried about where I draw that vector right now, but there's some horizontal force acting on that projector. So I'll call this vector F for force and H for horizontal. There's my horizontal force pulling the projector back. There's some horizontal force and some tension in the rope that is counteracting the force of gravity that is keeping to keep this projector stationary in a state of equilibrium. And remember, force due to gravity is always equal to the mass in kilograms times the gravitational constant. So in this question, the mass is only 2 kilograms. So 2 times 9.8, and we get 19.6 newtons. That's the force due to gravity in this question. So let me just draw that vector. And remember, the force due to gravity is always going down. So force due to gravity going down with what force? With a force of 19.6 newtons on a 2 kilogram object. So this horizontal force and whatever the tension is in this rope, let me draw a tension vector. Remember, the tension vector is going to be going the opposite direction away from the mass. So my tension vector, I'll do this one in green, is going to be going in this direction along the rope, and I'll label this T for tension. So this horizontal force and this tension vector have to add up to the exact opposite of the force due to gravity for this system to be in a state of equilibrium, right? Because those three vectors so this vector, and this vector have to add up to the 0 vector for the projector not to be moving, which means that the blue vector and the green vector have to add up to the opposite of the gravity vector. So let me set up my vector diagram where I position the horizontal force and the tension force tip to tail so that the resultant force equals the exact opposite of the force due to gravity. So I'll do that over here. So make sure when you do your vector diagram, you keep their directions exactly the same. I don't know what their magnitudes are yet, right? That's what we're actually solving for, but keep the directions exactly the same. So I know that that horizontal force and this tension force have to add up to the exact opposite of the force due to gravity. So same magnitude, so still 19.6, but it's going to be in the opposite direction. That's the only way that this system could be in a state of equilibrium. So here we go. Let me just make this system a little bit bigger so we can label it a little easier. And now let's figure out what we know and what we're trying to figure out. So I'm trying to figure out the magnitude of the tension vector, and the magnitude of the horizontal force. I believe that's what the question asked for. It says find the magnitude of the horizontal force and the tension in the rope. So I need to figure out the length of that side and the length of that side in this triangle. Now in this triangle, I do know the length of this side. I know it's 19.6 newtons. 19.6 newtons. Now, I have a right triangle where I know one side. I don't know either the other two sides, and I don't know a reference angle. In order to figure out the length of the other two sides, I'm going to need to know one of these two angles. So let's look back over to our position diagram and see if there's any way we could figure out what one of these angles in this triangle are. Notice this tension vector here. I could figure out what angle it makes with a horizontal line by calculating this angle in this right triangle that I'll highlight here for you. So in this right triangle, if I calculated this angle, that would be the exact same angle measure as this angle here, because here's tension 1 with a horizontal line. So if I could calculate this angle, it's the same as that angle. Okay, so how do I calculate that angle? Well, if we look at that outlined yellow triangle I have here, that triangle, we know two side lengths of the triangle. I know adjacent to the angle and I know hypotenuse. So I could calculate the angle by doing the cosine ratio because it's a right triangle. So cos theta equals adjacent 2 over hypotenuse 5. And then I can calculate theta by doing inverse cosine of that ratio. It's about 66.4 degrees. So if I go over to my vector diagram, I now know this is 66.4 degrees. So I could then calculate the magnitude of either of those vectors by using SOHCAHTOA because I have a right triangle. So from this reference angle, this is the adjacent side, this is the opposite side, this is the hypotenuse. So let's use SOHCAHTOA and solve for the magnitudes of the missing two sides. So let me solve for the magnitude of the tension first. So if I want the magnitude of the tension from the reference angle, I know opposite and I want hypotenuse, so that would tell me to use the sine ratio. So sine of the reference angle would equal opposite, 19.6, divided by the hypotenuse, which is the magnitude of the tension. Make sure you have your absolute value symbols here to indicate we're finding the magnitude. And then rearrange this to isolate the magnitude of the tension. That's 19.6 divided by sine 66.4 degrees. And then we would get the magnitude of the tension. So let me calculate that. It'll be an approximate value. It's about 21.4 newtons, so that's the tension in the rope. And now if I want the magnitude of the horizontal force, well, that's adjacent to the reference angle, and we know the opposite side, so we should use tan. So tan of the reference angle would equal the opposite side, which is 19.6, over the adjacent side, which we want the magnitude of that horizontal force. So use your absolute value symbols to indicate we're doing magnitude. And we can isolate the magnitude of that horizontal force by switching it with tan of 66.4. And then I'll calculate this and get an approximate value for the magnitude of the horizontal force. It's about 8.6 newtons. So for this system to be in a state of equilibrium, I know that the horizontal force is going this direction with a magnitude of 8.6 newtons, and the tension in the rope is going in this direction away from the mass with a magnitude of, I believe, 21.4 newtons. So make sure you go to the link in the description to get a copy of the practice questions, because the only way to get good at these questions is just to try lots of variations of them so you can find patterns in how you solve them and get good at your overall problem solving skills and get good at drawing your position and vector diagrams. So that's it.